All right, well, thanks for coming. Does anybody have any questions about anything before we start? Just keep on going. Okay, keep on going with file review then. I'm sorry?
How do you know if something is diamagnetic?
We are going to cover that later.
Oh, okay.
So that's coming up. The paramagnetic means unpaired electrons, one or more unpaired electrons. Diamagnetic means they're all paired. So, but we will cover that. I have problems on that coming up. So next concept to remind you is to connect stoichiometry with heat of reaction. So what mass of methane must burn to have 267 kilojoules of heat? So you can do a dimensional analysis, 267 kilojoules times mole CH4 to 802.3 kilojoules. And I'm getting that by the reaction here. 1 mole CH4 to release 802.3 kilojoules of heat. And then it's 16 grams CH4 per. Did you want the answer or just a setup?
Use the
Answer? All right. As you wish. Seven divided by 802.3 times 16 is 5.32 grams. So, all right, so any questions on how to do this one? The point is to connect the heat of a reaction to the stoichiometry. So, and all right, why don't you try 61 then? Use grams instead of kilograms. And nitromethane, so 12 plus 14 plus 32 plus 3. So what is that? That's 26, 58, 61 grams per mole. Doing that right. Okay.
But if you go above the potentially just 1,000 times.
I did it right.
Okay.
All right, anybody have any questions with these? Nope. Okay. So we'll just do A and B here real fast. Calculate the frequency of each wavelength, of each wavelength, and then the photon energy. So it's actually backwards. C. Jeez, why is this thing? Because the memory's getting full. C is lambda nu, so that implies frequency is speed of light over wavelength, which is 3 times 10 to the 8th meters per second, divided by 632.8 times 10 to the minus 9 meters. And now my alright. 3E8 divided by 630.8E minus 9. And this is 4.74 times 10 to the 14 hertz. And energy is H nu equals 4.47 times 10 to the 14th times 6.626, and this is 1/seconds, times 10 to the minus 34 joules times second. 3.14 times 10 to the minus 19 joules. So, okay, these are probably pretty straightforward for you, but I thought it'd be nice for you to go ahead and do a review on this one. I'll go ahead and take a picture. For that, so why don't you try B, the photon energy and the frequency.
Yeah, it looks like minus 9. Okay, good. And this multiplied by H. 6.626 times 34. I don't know what that is. It's hard to get to. Still glare. From the projector itself. That's for confusing. So you'll be given what's in the equation sheet is also in the list of concepts. You're allowed to ask what's H in the test as well.
So anybody have any questions with this one? I'm gonna move on. Okay, so what are the possible values of each value of n? So L exists up to n minus 1. So for A, it's 0. For B, it's 0 and 1. And for C, it's 0, 1, and 2. So what is it for 4? 0, 1, 2, and 3. Yeah. So everybody get that? Okay, and 61. Which set of quantum numbers cannot specify an orbital? So if n equals 2, L can be 0, 1. L being 1 is fine. If L is 1, M sub L can be minus 1, 0, or 1. That one's fine. For B, n is 3. L can be 0, 1, or 2. 2 is fine. If L is 2, M sub L can be minus 2, minus 1, 0, 1, or 2. 0 is fine. That's okay. So for C, n equals 3. L can be 0, 1, or 2. L equals 3 is not possible. So C cannot specify an orbital. D, if n equals 4, L can be 0, 1, 2, or 3. 3 is fine. If L is 3, M sub L minus 3, minus 2, minus 1, 0, 1, 2, 3. 0 is fine. D is fine. So that makes sense? Anybody have any questions with that? So there is questions like that on the final? Okay. And then this is your question here, William, coming up. So write orbital diagrams for each ion and indicate if it's diamagnetic or paramagnetic. So for vanadium plus 5, we have to go to the periodic table. And maybe I should just start off by writing the diagram for vanadium. Okay, is it going to stay? So vanadium's right here. So vanadium's structure is argons. So 1s, 2s, 3s, 4s, 2, 3d, 1, 2, 3. So it's argons, 4s2, 3d, 1, 2, 3. So the plus 5 means it's going to rip off all of these 5 and have the same as argon. And argon is 3s2, 3p6. So am I going to, oh, it stayed. Vanadium is, oh. Argon, 4s2, 3d3. Vanadium plus 5 is going to be argons. Argons, which is neons, 3s2, 3p6. And if there were this is 3s, 3p, 1, 2, 1, 2, 3, 4, 5, 6. Like that. And since everything is paired up, this is diamagnetic. So, how we gonna start questions with this? How I did that? Okay, so let me do another one. So, B chromium plus 3. So chromium is here. And so chromium's electronic structure, it's going to be argons, 4s2, 3d, 1, 2, 3, 4. And then, well, here, I'll just go ahead and it's going to cancel out. It is, sorry. It's 2, 3d, 4. Okay. As I stated, chromium's is, here, I'll just move this down. Chromium's is 4s2, 3d4, and when the electrons are ripped off, they're ripped off of the highest end first. So it's going to remove the 2 electrons from the 4s and then 1 from the 3d. So chromium plus 3, the structure is going to be argon structure 3d3. So plus 3 means 3 electrons ripped off. 2 electrons are going to be ripped off from the 4s, and then 1 will be ripped off in the 3d. So it'll be 3d3. And then, so 1, 2, 3, 4, 5. This is the 3d, and the 3 electrons by Hund's rule will go in their own orbitals. And then this would be paramagnetic, because there are unpaired electrons. So, questions on how to do this one? Okay, why don't you try iron plus 3? So, there's iron. This is Fe plus 3. So that's the 4s, this is the 3d. You don't know what questions that you have to ask? Yeah, so the highest end first. So 4 is bigger than 3. 4 is the 1, 2, 3, 3, and then it's
takes 2 from the 4S and then moves to 3D stack. So 2 from the 4S and then 1 from the 3D. That's why it's 3D. Yeah. And they're all one pair. So it's very magnetic. Makes sense. If you have degenerate the same energy, you got like small bus sequels sometimes too, like if you rent a bus. Then bus, you get your own seat and someone owns the bus, you're like, you actually person sits next to you. Seat, right? Electrons the same way, they negative charge, they like to have their own space, so they fill all the time and then they're all filled and they It would be a chart that's filled out. I forget the question was. I think it's you're given a normal diagram.
Wait, so on the 2?
Each row. Hydrogen helium's one shell, lithium to neon shell 2, sodium to argon's shell 3. So it's gonna be in the
There's no way of knowing the names of the world. Why is it like 4S 3D?
Yes. You have to memorize the 4S. Scantium is the 3D. Yep, you got it. I guess. So we're given this. You can see that's you can see 3 is 3S2, so then you only has 4. Or each 2 block is
Well, I'm
These are
sorry,
lines.
I mean the shell.
It's hard to say which one would be shell because
But this is 5, or this is S. Here to here is D, here is here, and that's true for each row.
then it goes for 6 and 7. It goes to here and then it goes to the F.
Because that's just
Lambda, and so 57 and 58.
So those.
So this is
Does it go all the way up?
So this is not on the test, but like copper is an exception. It's for a small 3D10, but the exception is on 1.
So, writing in the so for the first one, you labeled them, you went up, down, up, down, down, up, the other ones you get to them.
Yeah, numeral ones for the
Yeah, and so that comes
that
from.
are not, you know, that's start
Like,
so it's the 3Ds.
I have one.
Yeah. Or you know, you sort of these are so you sort of like say your person is the second person is the full. Usually the person has even 3 It's only when there's a 4 So they're trying to say so there's no sort of the same fraction and then it's
Okay.
if
Oh,
you're all each
If
of you
it's-
also So let's fix that.
Okay. How would I do that?
Cadmium plus 2. You find cadmium. Okay. So cadmium is going to be kryptons. This is 1, 2, 3, 4, 5. 5 is 2, 4 E, 10, 30. So cadmium 40, 10. And then the plus 2 means it's going to rip off from the 5s first. So these electrons will be ripped off. And then cadmium plus 2 is going to be krypton 40, 10. And 40, 10 has all those paired up. So it's that.
It's krypton because it's consistent.
Yeah, it's noble gas. This is that's the full shell.
So ripped off.
Yeah.
Yeah.
Plus 3 then it was the rip off. So that would be 349. That's all. 5 is 0. Okay.
Alrighty. So, arrange these isoelectronic series in order of decreasing radius. So, isoelectronic means same electrons. So each of these have same number of electrons, And if you look at the number of electrons and the number of protons, so here, isoelectronic means same number of electrons, and these, oh geez, I didn't tell you the number of electrons. It's 10. I didn't do my chart right. So each of these have 10 electrons, but they have different number of protons. So because of that, the smallest one is going to be the biggest number of protons. The biggest number of protons is going to draw on the electron cloud. And the least number, that's the one that's really big. So the size, it's in decreasing radius, it's going to be O2 minus is bigger than fluoride, bigger than sodium ion, bigger than magnesium plus 2. Does everybody get this one?
See that last part again?
Well, about what? The size?
Yeah.
So do you get that each of these have 10 electrons, and what's different is the number of protons? So the smallest one is magnesium because it has the most number of protons, and the electron cloud's going to be drawn towards the positive charge. And then oxygen with the least number of protons, it's going to be the largest because it's doesn't have a positive nucleus to keep the electron density. It just kind of flies out. So, does it make sense?
Yeah.
Please. So oxygen, well, it could be 8 valence, or oxygen has 8. It's the 8th element. So the minus 2. So then 8 plus 2 is 10. Yeah. Or you could say 8. It's 8's valence if you wanted it that way. And also 73 element with the highest first ionization energy. Oh, it's easier for the periodic table. Okay, I guess I could take a picture of the periodic table. So choose the element that has a higher first ionization energy, or bromine or bismuth. So here is bromine and here's bismuth. And the trend is up and to the right. That's the positive direction for that. So bromine here is both up and to the right from bismuth. Therefore, it's got the higher first ionization energy. Okay, and then sodium or rubidium. So here is sodium, here is rubidium. So sodium is higher than rubidium, so therefore it's the higher the first ionization energy. And arsenic or acetine. So here is arsenic, here is acetine. You can't tell that from the trend, and that's not on the test. Ambiguity is not on the test. You have no idea from the trends. And phosphorus or tin. So, well, that's going to be the same as bromine or bismuth, because phosphorus is here and tin is here. So it's that, up and to the right. So if it was something like boron and fluorine. So fluorine is to the right, so it would be the higher. But you won't be given a question like arsenic and acetine because that's unknown. Well, it's not unknown, but you have to look at the table. It's conflicting. Okay, so I guess. So first one here, let's start with 72. And these all have 36 electrons. You could probably logic your way through this without the periodic table, though, because if they all have the same number of electrons, the more positive ion is going to have the more nucleus, so or the more protons in the nucleus. So strontium is going to be first, then rubidium, then bromine, the less negative, and then selenium with the next negative. So, does that make sense? Not really? Okay. All else fails, use the chart. So So remember, when you make an ion, you rip off the electrons. So if you look here at strontium, strontium's right there, number 38. The atom has 38 protons and 38 electrons. The +2 ion has -2 electrons, 36 electrons, but still 38 protons. So like that, and then I've written them in increasing order, just as is. So the smallest one is the one with the more protons, and the largest one is the one with the least number of protons. Okay, so tell me then for ionization energies for each of these. I do apologize if anyone's colorblind. I find it easier just to color code things. So silicon and chlorine. Chlorine's to the right, so it's got the higher first ionization energy. Antimony and phosphorus. Phosphorus is higher, therefore has the first. And indium and germanium, it's both up and over, up and to the right, so it's definitely more positive. So, and you don't have to know any of the exceptions or the ones that are ambiguous. So, questions with this one? So just the logic of it. Okay. Use formal charge to identify the better Lewis structure. So formal charge here. With the formal charge, you get half of bonding electrons and all of lone pairs. So for carbon here, the carbon gets one electron from each of the bonds. So I'm going to zoom in. So it gets one electron from each of the bonds. Carbon starts with 4. It has 4. It has a formal charge of 0. Sulfur here has 1 from each of the bonds, and then it has 4 lone pairs. It starts with 6. It has 6. It has a formal charge of 0. The sulfur here, it has starts with 4. It starts with 6. It has 4. It has a formal charge of +2. Carbon starts with 4, has 6. It has a formal charge of -2. So because of that, this is the better Lewis structure because it has the lowest formal charge. So does that make sense? Does anybody have any questions? All right, try it for this one. So each line really means 2 electrons. And if it has a line, that means it gets half the electrons. I didn't even include the hydrogen. They all have 1. And they don't change on each side. It's the carbon and the sulfur that switch. And also, generally speaking, carbon tends to bond with 2. Nitrogen and phosphorus tend to bond with 3. Oxygen, sulfur tend to bond with 2. Halogens and hydrogen tend to bond with 1. So that's the other thing. That's the other hint to this is that the carbon bonding with 4 and the sulfur bonding with 2 is the better one. So questions with this? Okay, ethanol, the possible fuel. Use the average bond energies to get the heater reaction for the combustion of ethanol. So, it helps to write the Lewis structure. I usually write it out. I usually write out the whole thing just to make sure I don't mess up a bond. as well put the dots on there because. Okay. So it's the sum of the bonds broken minus the bonds formed. And so what bonds are we breaking? We are breaking 5 carbon hydrogen bonds. Plus 1 oxygen hydrogen bond plus 1 carbon-carbon single bond plus a carbon-oxygen, 1, plus 1 carbon-oxygen bond. So I'm running out of colors here. Three oxygen double bonds minus, I guess I can do black. 4 oxygen carbon double bonds plus 6 oxygen hydrogen single bonds.
So you see here you got all the bonds. There are 5 carbon hydrogen single bonds, broken 1 hydrogen oxygen single bond, 1 carbon single bond, 1 carbon oxygen single bond, and 3 oxygen double bonds. And we form 4 carbon oxygen double bonds and then 6 oxygen hydrogen single bonds.
And then you just take the average bond energy chart and you put in those numbers and then you get the, you sum it out. You apply the equation there and you get it. So let's see if you can do this one here. So 83. And I will even give you the Lewis structure for water and CO2, like so.
No, it means they're ripped apart. Yeah, color code. Yeah. Two loggers, so you can bring forward. I left them out. I'm gonna grab some. There for your test. I was threatening bodily harm during office hours. Two girls shot it. They're pretty interesting, so they're same thing. It takes energy to rip apart bonds and then get them in for it. Yeah. I didn't bring hydrogen, but it's just. Andromedas. I can't remember if it's ancestral or something.
All right, we're flying through. Good. Good. So this one, hybridization. And I specifically just looking at the carbons. So I know it says each interior atom. I can do that if you want, but it's this. Okay, so this one here, this carbon, has 3 bonding groups. So let me start off with this carbon here. You can't see that. That'd be yellow. You see yellow? Yes, you can see yellow. So this yellow carbon here, it has 3 bonding groups around it. So the 3 bonding groups and the no lone pairs, that's planar, and that's sp2. And you will be given, so you will be given, which chart? 10A. You will be given this chart and also the hybridization chart. So you will know that 3 things, all bonding is planar electronic geometry. And then you will also be given what's that chart? Oh, this one here, sorry. And you're also given this chart so that you know planar geometry is SP2. Did I put SP2 or did I put SP3? Shoot. Yeah, SP2. So 3 things, all bonding is planar geometry. That one's SP2. And looking at this carbon, it has 4 things, all bonding. So that means tetrahedral geometry, which means SP3. Likewise, this carbon here has 4 things, all bonding. That makes it SP3, tetrahedral geometry. And although I might as well do the nitrogen is in fact interior, so I'll go ahead and do that one. It also has a lone pair here. So this nitrogen has 4 things, 3 bonding, but either way it's tetrahedral geometry. This one is also SP3. Does anybody have any questions on how to do this one? So in general, so if it's linear, it's SP. Planar, it's SP2. Tetrahedral, SP3. Why don't you tell me for this one, it's Christmas coming up, so I'll go ahead and do red and green. I should have picked a different one. It's just going to be departments. Yeah, this is.
So if we're see behind it's usually it's a benchmark.
No, it's only 3 SPs. There's SP3D. You didn't? You got it? Oh, you got the other stuff right there. Yeah. Counts as screw. So this one, it's going to be SP2, right? And so is that oxygen. So is that oxygen. Terminal oxygen. Doesn't work well.
Okay. So here's caffeine. So the sigma and the pi. So a single bond is 1 sigma bond. A double bond is 1 sigma, 1 pi. A triple bond is 1 sigma and 2 pi bonds. So the number of sigma bonds in this molecule. So not listed, each of these is 3. And that's 1 there. So the rest though, each bond is going to be a sigma bond. So there's 3 here, because the CH3 is, and it's not going to be a molecule this big. You have to do this with a molecule that's smaller, and it's going to be spelled out for you. The CH3 looks like this. So there's 3 bonds in each of them. So 3, 6, 9, and then 10 there. So 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So 25 sigma bonds. Did I miss any of them? Now pi bond is each from one of the double bonds. So the pi bonds, there's 4 double bonds, therefore there are 4 pi bonds. So, questions on how to do this? It's just one of those, another one of the things you have to remember. That a single bond is a sigma bond, a double bond is a sigma bond and a pi bond, and a triple bond is a sigma bond and 2 pi. And the number of pi bonds here, because there's 4 double bonds, then it's just 4 pi. And then the single bonds, you have to count up all the bonds. I mean, in the double bonds, it's a sigma and a pi. So you just count the number of bonds. So, questions with this one? All right, try it for aspirin. NL. This is going to be 7 right there, but oh, 8.
Close.
Alrighty, it is 1 minute to close, and request from the department head says to please fill out your evaluations, course evaluations, and also to register for your classes in the fall. So, if I may, you guys have been an amazing batch of students. You're the best batch of students I've had in several years, and I've been teaching for 13 years. So hopefully it's been as enjoyable for you, and I mean all 3 sections, the online and 2 face-to-face. So you guys have performed very well. So hopefully you feel the same way. You don't have to tell me, but so anyways, I am done then, and final is a week from today, same time, same place. If anyone can't make it, please let me know and I can put you in the testing center. So, okay, well, goodbye for now.